Hi, my name is Sammy Cherna,
And my name is Philip Berzanowski.
and this is our 6832 final project. We worked on trajectory optimization for the Furuta pendulum. In particular, we looked at how we could get the Furuta pendulum to avoid obstacles.
The motivation for using the Furuta pendulum as our model was fundamentally the simplicity of the model. It was a simple extension into problems in 3D and only required one actuator and two joints, meaning it was a very favorable model for actual physical implementation. That meant that overall, it allowed for the dedication of more effort into the control modeling. At the top is a diagram of our Furuta pendulum model. At the origin, there's a fixed joint named the shoulder. A rod connects from the shoulder to the elbow at an angle θ1 in the XY horizontal plane, from which point another rod extends perpendicular to the shoulder to elbow joint to the hand. The equations of motion for the system are below. The inputs on the right, τ1 and τ2, are the actuation in the shoulder and elbow respectively. However, as we will be using this as our underactuated model, we will only be providing input into τ1. This entire system was implemented as a URDF in our programming, which is a universal file format for describing physical objects. The parameters for the inertia matrices and masses were referenced from papers using this implementation.
Our first control task for the Furuta pendulum was implementing a balancing LQR controller. LQR is a method for linearizing the system's dynamics around a fixed point and implementing a quadratic cost in order to stabilize the system around a fixed point. Here you can see a video of the pendulum successfully balancing at the upright position. Once we had the balancing LQR controller working, the next control task we looked at was getting the Furuta pendulum to balance at the upright, starting from any initial state. Typically, this is done using an energy shaping or swing up controller, in which the energy in the system is pumped up until the pendulum is close enough to the upright position, at which point the balancing LQR controller kicks in. Instead, we looked at trajectory optimization, which takes the initial state and the desired final state and formulates an optimization problem in order to find the optimal control trajectory to get the pendulum from the initial state to the desired final state. In particular, we looked at a technique called direct collocation, which breaks up the state trajectory and control trajectory into piecewise polynomials. This is a convenient way to formulate the optimization problem in terms of the values of the trajectory at breakpoints. The dynamics of the system are then enforced at the collocation point in between each polynomial segment. From this point, we're able to add additional constraints on the trajectory at the breakpoint. Here, we can see a clip of what happens when we take the control trajectory found by direct collocation and providing it directly as an input to the plant. As you can see, it does not actually make it to the final position at the upright.
The reason why direct collocation alone does not work is partially because of numerical accuracy and fundamentally because it lacks a stabilizing controller along the trajectory. To remedy this, we use finite horizon LQR, which follows the same implementation as a standard balancing linear quadratic regulator. However, instead of linearizing around a single fixed upright point, the finite horizon LQR linearizes around discrete points in the trajectory, with the cost being altered to factor in the desired states and control inputs. Here is an example of the finite horizon LQR being combined with the direct collocation, which stabilizes. Once we had trajectories optimized and stabilized using finite horizon LQR from any initial condition to the upright state, our focus turned to more complicated trajectories. For example, we have a trajectory here stabilizing every 9 degrees, alternating in the upright and down positions. To make full use of the state space we were working with, we found that the best solution was to go from -π to π in θ1, as the solver was not actually aware that those were equivalent. So in that way, using for initial trajectories, linear interpolation between those points, we can have the Furuta pendulum complete a full circle in the horizontal plane. Furthermore, we could then ask it to complete loops by concatenating these full circular trajectories. Another thing to consider was that the upright position for the pendulum was for θ2 equal to, again, either -π or π, meaning that when we wanted to stabilize from arbitrary points, we had to consider which side we would want to initiate it in, as that would influence the direction of its swing during the trajectory.
Once we successfully had the Furuta pendulum executing complex trajectories in space, we wanted to see if our trajectory optimization tools could find paths which actually avoid obstacles in space. We looked at a few different kinds of obstacles, but eventually we settled on spherical obstacles because we could implement the spherical obstacle avoidance as nonlinear constraints in the trajectory optimization by looking at the distance between the center of each sphere and the hand of the pendulum and enforcing that they stay far apart. Here we can see an example of a trajectory found by our system which successfully avoids the spheres. We have one sphere in the bottom right front octant and one sphere in the top left back octant. So we can see how the pendulum just narrowly swings around the sphere, but does not actually come into contact with it. And that is our 6A through 2 final project. Thank you for watching.
Thank you.